I'm Jono Buchanan. Now then, as discussed in another episode, is music an art subject or a science subject with maths at its core? Well, it's both. We tend to think about making pieces of music, composing, producing as artistic endeavours, but underneath and inside every single note that we play is a whole world of maths. And to begin to understand a little bit why that maths is relevant to the music that we make, it's really worth beginning to understand that frequency and pitch are the same thing. Now then, what do I mean by those two words? Well, here's a pitch, we're going to call it A. And it just so happens that this pitch, this A, has a frequency of what we refer to as 440 hertz, 440 cycles per second. So the waveform at the heart of this note vibrates 440 times per second. Now, if it does it less than 440 times per second, the pitch drops. And if it does it more than 440 times per second, it rises. So in other words, the frequency of this note is unique to this note, and any lower frequency produces a different pitch. Okay, so effectively, if we're willing to accept that that's true, that the middle of this note is vibrating 440 times per second, what do I mean by the middle of this note? Well, to understand that, what we're going to do is to have a look at this EQ, which is going to allow us to hone in on 440 hertz. And what I'm going to do is to press the little speakers button, which means that we're going to solo an incredibly narrow group of frequencies around 440 hertz. Here is the same note. Now, this is a very different musical experience. This is much more like a sine wave now. And what we're doing is we are effectively soloing what we refer to as the fundamental, one of the harmonics of the experience of this note. What are harmonics? Well, it turns out that when we play a note, we don't just play its fundamental frequency. What happens is that its frequency, the fundamental, triggers a whole series of other notes that are mathematically related to the fundamental frequency that we play. In other words, multiplications of the core frequency are going to be triggered every time we play a note. So if 440 hertz provides us with the A that I'm playing, if we were to multiply that number, then effectively we're going to hear the other harmonics that are present in the note. So because 440 isn't a times table that we tend to learn in school, let's use a calculator. What we're going to do first of all is to times this by 2 to double the frequency, and that's going to produce a frequency of 880 hertz. So what I'm going to do is I'm going to keep pressing A, but what I'm going to do is to change the frequency that we're going to listen to 880. I'm going to solo it, play the same note, and what do we get now? We get this note. So clearly, if I play this note is also triggered. And actually we can see that. I can see that when I play this note, this first harmonic, which is here, the first harmonic being triggered by the fundamental frequency, is here. And I can actually see that there are some other spikes that are coming out as well. And I'm willing to bet that those are going to be the other harmonics that are present in my sound. But what are they? Well, they're also going to be multiplications of my core frequency. So if I come back to 880 and I times it by 2, so we get a further multiplication of the core frequency that was 440, what we're going to do now is to discover that that frequency is 1760. Let's type that in here and let's solo it and let's play the same note again. Sure enough, we've got another A. So what we've now got is a series of notes that are playing as a result of playing this note. We know that this is our original note, we know we've got this note playing, and we know that we've got this note at a frequency of 1760 hertz, which we can see lighting up within the EQ. But hang on a minute, if we're using 440 hertz as our unit, this was 880 and this is 1760, there must be one in the gap. There is a multiplication of 440 that's somewhere between 880 and 1760. Let's come back to 440 for a second. And what we're going to do is we're going to add 440, and that's going to take us to 880. And if we add another 440, okay, so sure enough, there's going to be some sort of harmonic at 1320, 1.32 kilohertz. So let's type that in next. Let's solo it and let's trigger our note and let's see what note this is. Okay, so this is not an A, this is E, and it's this E. So what we've discovered so far is that by playing this note, we're triggering this note and this note and this note. They're all part of the experience of this note on the piano. Okay, so we already know that if I add another 440, we get to 1760, which we know is this A. So what happens if we add another 440? Okay, we get to 2200. Let's go there next. Let's solo it and let's see what note we get now. Well, you can see on the screen underneath this frequency that this is C sharp 7, this note here. So we've got this note, this note, this note, this note, and this note all being triggered from our A, our first A. Now then, just for a moment, let's reorder these notes somewhere a bit more sensible. So we've got A, we've got E, we've got C sharp. Okay, so that is an A major chord. Let's have a look at it another way. We've also got an octave, a fifth, a fourth, the E to the A is a fourth, and now we've got a C sharp, which is a major third. We also know, and we're beginning to understand, that each frequency triggers the octave above, right? We know that A triggers A. So if there's an E, there's going to be an E there too, which is going to be our next harmonic. And the amazing thing is that next we get the G. Now, suddenly, we've got a chord that is instantly recognizable as an A7. And the frequencies keep going. They just get closer and closer together. They become microtones. Now, if I trigger this note and we have a look at our EQ, we know that this is our fundamental frequency, but we can also see that there are notes underneath the fundamental that are also triggered as a result of this note playing. But we can see the individual spikes that make up the harmonics relative to this sound. Why do harmonics matter? They matter because they tell us what we're listening to. Now then, what do I mean by that? Well, we've already discovered that if I solo around the fundamental frequency, what we get is this very thin, very sine wavy experience. And if I was to take that even further so that we were only listening to the frequency of 440 hertz, the character of the sound we were listening to would be completely lost. It wouldn't matter if that note was being triggered on a piano or a violin or me singing it or me having recorded a truck driving outside that happened to contain 440 hertz. Another way of putting what I've just said is, if I was to take all of those instruments and put them side by side and solo around 440 hertz, they'd all sound the same. They'd sound like a sine wave playing 440 hertz. The character of the sounds that we play is entirely determined by the harmonics that are triggered by each individual note. The harmonics of a violin are different from a piano, so a violin sounds different to a piano. A trumpet sounds different to a violin and a piano because, again, it has different harmonics. And our brain's ability and our ear's ability to detect the harmonic content of any sound around us is amazing. Here's an example. You probably know tens, if not hundreds of people. And if someone calls your name from behind you and you haven't seen them yet, more often than not, you know who that person is by the character of their voice. Now, they're not speaking a different language. They're speaking a language that you understand. 200 people could say, hi, but the tone of that person's voice, you can immediately tell who it is who said it. Our voices are our capacity to hear voices, but to hear sounds and frequencies and how those things relate together is unbelievably complicated. And it's amazingly natural how good we are at picking apart and hearing different frequencies and how they relate together. And we might not think, oh, that person's speaking to me with a pitch bass of G sharp, but we're very good at determining and pulling apart the frequencies in their voices. So what we've done in this video is to discover that there is maths behind the pitches of the notes that we play. That the note A means A, and from there we can put an A in an F major chord, or we can put an A in a D major chord, or we can put an A in an A minor chord, or we can put it in any chord we like, and we're talking about the language of music. But if we talk about A, we're talking about the frequency of 440 hertz if we play it right here. And what we discover here is that the frequency content of this note is central to our understanding, not just of this pitch, but of also the chord that is triggered by its harmonic content.